Welcome to GATE 2025 solutions. In this video, we are going to discuss GATE 2025 questions from Instrumentation Engineering paper from the subject Electric Circuits. Question number 1. This is GATE 1 mark question. The circuit shown in figure A can be represented using its equivalent T model as shown in figure B. The value of the inductances in the equivalent T model are. Let us recall a small concept, that is T equivalent of ideal transformer. T equivalent of ideal transformer for both the cases, that is mutual adding and the mutual opposing, are shown here. If you want to know how to derive the T equivalent of ideal transformers, please comment below. We will try to explain the proofs of these circuits. With the help of these circuits, now let us go to the question and continue to solve the problem. By comparing these circuits with the circuits given in question, we can calculate the values of L1, L2 and L3. Comparing both the circuits, we get the value of L1 as 7 Henry. Similarly, L2 as 6 Henry and L3 as minus 4 Henry. Therefore, option A is correct. Question number 2. This is GATE 1 mark question. Three parallel admittances connected in parallel with a voltage source draws a total current Is from the source. The currents flowing through each admittances are given as Ia, Ib and Ic respectively. It is also given that I is equal to Ib plus Ic. We need to find the phase relation between Ia and Is. Let us draw the circuit from the data given in the question. To calculate phase relation between I and Is, we need to calculate the currents Ia, Ib and Ic. To calculate this, let us consider Ohm's law. From Ohm's law, voltage is equal to current into impedance. From this, we can get current is equal to voltage into admittance because impedance is reciprocal of admittance. From this, we get I is equal to V into Y, where Y is admittance. From the given circuit, I is equal to voltage 10 angle 45 degrees multiplied with admittance. Since admittances are connected in parallel, we can add them directly. To calculate current I, the admittance become Yb plus Yc, that is 0.3 plus J into 0.4. Simplifying this, we get the value of I as 5 at an angle 98.13 degrees. Similarly, to calculate the value of Is, multiplying voltage 10 angle 45 degrees with the total impedance Ya plus Yb plus Yc, we get the value of Is as 3.6 at an angle 78.69 degrees. Now let us try to draw phasor diagrams for the currents I and Is. From the phasor diagram, the angle between the currents I and Is is 19.44 degrees. So we can say that I leads Is by 19.44 degrees, which is also same as Is lags I by 19.44 degrees. Therefore, option A is correct. Question number 3. This is GATE 2 marks question. The circuit is given. The switch is opened at t is equal to 0 seconds. We need to calculate the current I of t at t is equal to 2 milliseconds. I of t is the current flowing through 120 ohms resistor. This is the question from transients. And also this is an first order circuit. We can calculate the value of current flowing through the inductor by using this formula. To calculate the current I of t at t is equal to 2 milliseconds, we need to calculate the final value of current flowing through the inductor, initial value of current flowing through the inductor, and also the time constant of the circuit. After the switch is open, that is for the time t is equal to 0 plus, by using KCL, we can say that 10 milliamps is equal to I of t plus IL of t. First, let us calculate the initial value of current I of t at t is equal to 0 minus, that is before switching action is done. The circuit can be represented as shown here. If you observe the circuit here, 10 amps ideal current source is short circuited. Therefore, current flows only through the short circuited path. That means current does not flow through resistors and inductor. Therefore, these resistors and inductor becomes redundant. And hence, we can say that IL of t and I of t are 0 milliamps. Now, let us calculate the values of currents at final steady state value, that is at t is equal to infinity. During the steady state value, after the switching action is done, the inductor behaves as short circuit. Therefore, the given circuit can be represented as shown here. From this circuit, we can calculate the value of current flowing through the inductor by applying current division rule. From this, we can get the value of current flowing through the inductor IL of t as 6 milliamps. Now let us calculate the value of current flowing through 120 ohms resistor, that is I of t is equal to 10 milliamps minus IL of t, which is equal to 4 milliamps. Keeping these values aside, now let us calculate the value of time constant. To calculate time constant, we need to replace the sources with their internal resistances. If it is ideal voltage source, then we can replace it as short circuit, and for ideal current source, we can replace it with open circuit. Redrawing the given circuit by replacing the sources with their internal resistances, we get the circuit as shown here. From this circuit, to calculate time constant, we need to calculate the resistance seen through the inductor. Therefore, the resistance becomes 40 plus 120 plus 40, which is equal to 200 ohms. And also we know that inductance is equal to 0.2 Henry. Therefore, tau is equal to 1 millisecond. We have obtained the values of initial value, final value, and also time constant. Now let us go to the question and calculate the value of current I of t at t is equal to 2 milliseconds. Let us note the values of initial value, final value of time constant aside. We also know that at t is equal to 0 plus 10 milliamps is equal to I of t plus IL of t. Let us recall the standard formula which is used for first order circuits. To calculate the value of current flowing through the inductor at t is equal to 2 milliseconds, substituting the values of final value, initial value and time constant, we can get the value of current flowing through the inductor IL of t as 5.18 amps. Now from using KCL, we can calculate the value of current flowing through 120 ohms resistor I of t as 10 milliamps minus IL of t, which tends to the value 4.81 milliamps. Therefore, the current I of t at t is equal to 2 milliseconds is 4.81 milliamps. Question number 4. This is GATE 2 marks question. For the circuit shown in the figure, the active power supplied by the source is. First, let us calculate the equivalent impedance of the given circuit. If you observe here, these two branches are connected in parallel. If we calculate the equivalent impedance of these two branches, we get the equivalent impedance as 5 plus j5 ohms. Now the circuit can be represented as shown here. Now if you observe here, these impedances are connected in series. Since these impedances are connected in series, we can add them directly. Therefore, the final circuit becomes as shown here. Now let us calculate the active power supplied by the source. We know that active power P is equal to VI cos phi. From Ohm's law, we know voltage is equal to current into impedance. Now we can calculate the active power supplied by the source. P is equal to Vs square by Z into cos phi. Substituting the values of Vs and Z and solving the equation step by step, we can calculate the active power supplied by the source as 600 watts. Question number 5. This is GATE 2 marks question. In the circuit shown, the galvanometer has internal resistance of 100 ohms. The galvanometer current is. To solve this circuit, let us apply Thevenin's theorem. We can solve this circuit using many ways by applying mesh or nodal analysis, but Thevenin's theorem makes this problem easier. So let us apply Thevenin's theorem for this problem. Let us remove the galvanometer and redraw the circuit. By using this circuit, let us calculate the values of VTH and RTH. We know that Thevenin's voltage VTH is the difference between the nodes A and B. To calculate node voltages VA and VB, we can apply voltage division rule. By applying voltage division rule, we get the value of Thevenin's voltage VTH as 0.01 volt. And to calculate Thevenin's resistance, we need to replace the sources with their internal impedances. We can replace ideal voltage source as short circuit. If the voltage source is short circuited, then these two resistances are in parallel, and also these two resistances are also in parallel, but either of them will be connected in series. Therefore, we can calculate the value of Thevenin's resistance as shown here. The value of RTH becomes 1002.48 ohms. Keeping the values of Thevenin's voltage and Thevenin's resistance aside, now let us draw the Thevenin's equivalent circuit. From Thevenin's equivalent circuit, we can calculate the value of current flowing through the galvanometer Ig as Thevenin's voltage by Thevenin's resistance plus resistance across AB, that is the resistance across galvanometer. By substituting the values of VTH, RTH and the internal resistance of galvanometer, we get the value of current flowing through the galvanometer as 9 microamps. Question number 6. This is GATE 1 mark question. The working of the handheld metal detector most widely used by security personnel for human frisking is based on the principle of. Generally, handheld metal detectors used for human frisking is based upon the principle of electromagnetic induction. This process involves generating an alternating EMF. When this electromagnetic field interacts with the metal object, some eddy currents are induced within that object. These eddy currents in turn create a secondary magnetic field which is detected by sensors, and sensors triggers an alert. Therefore, from the given options, we can say that the working of handheld metal detectors used by security personnel for human frisking is based on the principle of eddy current generation in the metal object. Therefore, option D is correct.